Okay, so now that we've seen how to use stoichiometry and incorporate that into expressing the rate of a reaction, we're now going to take a look at how we can relate the rate constant, and the reaction concentration to each other. So remember when we talk about a rate law, well, we didn't talk about a rate law yet, but when we mention the rate law, this is a way to relate all of those things together. And if you look at a general equation, such as the one that we've seen previously, so A reacts with B to produce C and D, and we have our coefficients that we insert to balance the equation. The rate law is something that we can write that is going to relate the rate of that reaction to the concentration of the reactants that we have. Okay, so that's the first thing to keep in mind. This rate law that we're going to be generating and using relates the rate of the reaction to the concentration of the reactant. So in other words, we're just looking at these and how they affect, or we can use that to write this rate law. We're not really concerned about the products, writing the rate law. So a rate law for an equation like this would be equal to the rate equal to K. Remember, K is the rate constant times the concentration of one of the reactants. In this case, it's A, raised to a certain power. We're going to call that X for right now, times the concentration of the other reactant. In this case, it's B, raised to a certain power. We're going to call that Y for right now. Okay, so these are the concentrations that we mentioned of the reactants. And then X and Y, these are known as the order of the reaction with respect to, so WRT, with respect to each of those reactants. Okay, and those X and Y values, whatever they are, they need to be determined experimentally. Okay, they are not, you can't use stoichiometry to determine them. You have to determine them from experiment. Okay, so our general form for the rate law and all of the rate constant, the concentration, as well as the order of the reaction with respect to each of the reactants. If we sum together the orders of the reaction, we end up with the overall reaction order. The sum in this case of X and Y. Okay, so we've introduced a few terms here, and we're going to take a look at how we can experimentally now determine this particular rate law. All right, so if you remember back from, let's go back to the equation we looked at previously, way up here, we wrote out an equation such as this one that we had back here. Okay, this is an example of a rate law. So we have a rate equals a rate constant K times the concentration of one of the reactants, Br2. And then the other reactant that we had was a formic acid, HCOOH. Okay, and then this would be our X, and this would be our Y. So from our equation here that we have written underneath, so this would be our general equation above, it's based on the equation that we have, general equation, and then the one underneath here is what we determined from the experiment, right? So you'll notice that, yes, we have a similar expression. In this case, the value for X has to be 1, right? Because anything raised to the power of 1 is that thing. And we don't see the HCOOH in our rate law for this equation. So that means the value for Y here, if we don't see it, right, 1 is understood to be there. So the value for Y has to actually be 0, because anything raised to the power of 0, right, this entire thing here is 1, right? So you can say that this equation is first order with respect to Br2, it's 0 order with respect to HCOOH, and the overall order of this reaction overall reaction order, right, is the 1 plus the 0, the sum of the two things. So it's first order overall. Okay, that's how we sort of use those terms to describe the different components of the rate law for that particular reaction. So let's jump back down to a specific example, a different example, and we'll take a look at the reaction between fluorine gas and chlorine dioxide to produce FClO2. We have a balanced equation written here. And what we can do is we can perform several different experiments. In this case, we have 3 different experiments that we perform. We vary or we change the concentrations of each of the reactants, and then we measure the initial rate in each of these experiments, right? And remember, the initial rate is just the instantaneous rate at the beginning of that particular reaction. So in experiment 1, we have 0.1 molar F2, 0.01 molar ClO2, we measure the instantaneous rate. In experiment 2, we keep the F2 the same, we vary the ClO2, measure the rate there as well, and then experiment 3, we double the F2, we keep the ClO2 the same compared to experiment 1, and we record the rate there as well. So using this tabulated data, this set of data, we can now explore, we can actually determine all of those components of the rate law. So what we can do, first of all, is write the rate law expression for this. So we can say that the rate is equal to K, the rate constant, times the concentration of the reactant F2 times, I'm sorry, raised to a certain power, times the concentration of the other reactant, ClO2, raised to a certain power, Y. Okay, remember, stoichiometry or the coefficients don't come into the rate law expression. And we just look at the concentrations raised to a certain powers. So how do we determine X and Y? How do we determine X? I'm sorry, K, the rate constant? Well, what we can do is we can compare different experiments. Okay, and we want to compare experiments such that, so we're going to select ones where, like 2 experiments to compare, where one reactant concentration is unchanged, and then the other is varied or changed. Okay, so for instance, what we can do, first of all, if I just look at my data, I can select experiment 1, and I can select experiment 3. Right, and the reason why I want to select these is because between experiment 1 and 3, what we're holding constant here, right, is the concentration of the ClO2, right? So that's constant. And in those same 2 experiments, what we're varying, what we're changing is the concentration of the F2 in this case, right? The F2 concentration here changes. Specifically, it goes from 0.1 to 0.2, that's a doubling of that concentration. So what I can do is compare them directly. Okay, so if I have the concentration of F2 in experiment 3, and I divide it by the concentration of F2 in experiment 1, so I'm comparing these 2 values, end up with 0.20 divided by 0.10, that's 2, right? So that means here I doubled the concentration of F2. Okay, we didn't change the concentration of ClO2, so that stays the same. What happened to the rate? Well, if I compare now the rate of equation or experiment 3, and I divide it by the rate of experiment 1, so these are the values, 2.4 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3, and then we have our units molar per second. We see that that's equal to 2 as well. Here we see that the rate is doubled. Okay, so what does this mean? How do we interpret this? Well, we can say as the concentration of F2 is doubled, doubles, the rate doubles as well. Okay, so what that means is there's a direct relationship or directly proportional relationship between the concentration of F2 and the rate. Okay, so what we say is that then the value for X there be equal to 1. And when there's that directly proportional relationship, right, so we know as F2 doubles, the rate doubles as well. So that value for X there is 1. So we say it's first order with respect to F2. Similarly, we can look at the other reactant. So if we look at ClO2, so we can compare two reactions where the concentration of ClO2 changes. Right, so we compare reactions 1 and 2 now. Okay, so here we see that ClO2 changes, whereas F2 stays the same. So we can select those two. Those are two different experiments compared to the first example. And again, we can do something similar. So we divide the concentration of ClO2 in experiment 2 by the concentration of ClO2 in experiment 1. So that's 0.04 divided by 0.01, and that gives 4. So we quadruple, in other words, the concentration of ClO2. What happens to the rate? Well, we divide the rate for experiment 2 by the rate for experiment 1. We see that the rate gets quadrupled as well. Okay, so we can say as the concentration of ClO2 is quadrupled, you see that the rate is quadrupled as well. So that is also a directly proportional relationship. So guess what? The value for y there, we can say that it is first order in ClO2 as well. Okay, so the value for y there is going to be 1. So when we take those and we insert it now back into our general expression for the rate law, we can see now that the rate is equal to K, the rate constant, times F2 raised to the power of 1 times ClO2 raised to the power of 1. Okay, 1 is understood to be present, so we can simplify this, kind of clean it up a little bit. So the rate equals K F2 ClO2. Okay, so in all of these examples, whenever you see these in your homework and elsewhere, you'll usually be given a set of experimental data. You want to select two experiments to compare, and those two that you select should be ones where the concentration of one of those reactants changes, but the concentration of the other does not change. And you can see the effect that that has on the initial rate, or how that accompanies the change in the initial rate as well, to determine what the values for those exponents or those orders of the reaction are with respect to each of the reactants.